Welcome back to the lecture on drone systems and control. Our next lecture will be on PID controller. In this lecture, we will describe the structure and mathematical formulation of PID controller. We will go through individual effects of the components, proportional, integral and derivative terms or components of PID controller, and we will check that how these terms affect the system performance. We would try to interpret step response characteristics under different PID configurations. We will go through one example, which will be a MATLAB example. Okay. We will identify basic methods for tuning PID parameters to achieve desired control performance, though we will not go into much details of PID tuning. Okay. And we will try to recognize common applications of PID controllers for drone systems. Okay. So, what is the motivation behind choosing PID controller? PID, which is a kind of acronym of proportional, integral and derivative controllers, it is easy to understand and implement. It is, though it is very simple to understand and implement, it is very powerful method for engineering control systems. Okay. We can see PID control around 90% of industrial control loop applications, and we can see the applications in automotive systems, robotics, manufacturing, drones, etc. It handles real world problems because it has a very versatile nature, so it can compensate for disturbance, model uncertainties, noise, external noise, and also can take care of the desirable performance metrics. Okay. It achieves desired behavior in terms of stability, accuracy, speed. Okay. It balances key performance metrics. How? The proportional term mainly focuses on fast response. Integral term looks for zero steady state error. I hope you remember what is steady state error, because it was covered in the lecture on transient response. Finally, in derivative, the derivative component improves stability and damping. Okay. So, if there is some oscillatory nature in the response, then we can use the derivative component of PID control to bring that down. The oscillatory nature can be eliminated like that. Okay. So, PID control is effective for both mechanical and electrical systems. Okay. So, I will just go back to recap on feedback control system concept. We can remember that when there is no feedback loop around, then we call it as a open loop control system, right. So, the control action is independent of the output, and that is why there is no error correction mechanism. However, when we talk about closed loop or feedback control, then control action depends on the output, and the closed loop systems use the feedback method to improve the performance and accuracy. So, this is the feedback path, right. Yes, this is feedback, and compared with the input signal, we generate the error, which is the error can be represented as the reference input minus output, or the sensor version of the output, right. So, this is the error. That error is handled by the control system component in feedback control system, and it gives a error correction mechanism. When there is a feedback, we can see that the accuracy will be high, the stability can be improved. However, because of some complexity added into the system, the cost is higher. Okay. Fine. So, feedback control system is a process of taking a portion of the output and returning it to the input, right. That is where from we get the error. Okay. The system compares the actual output to the desired output. The difference is the error. Okay. And it is a kind of key component of modern control systems. So, if we remember, the block diagram was something like this, where this is the reference input. Now, this is the reference input. It goes, it gets combined with the negative feedback with the output signal y, and then finally the error is calculated, right. This error directly goes to the controller. Once the controller starts handling the error, it gives the command to the actuator accordingly, and the actuator will function in the desired manner, so that the drone behaves in the desired manner, right. That was the basic concept behind feedback loops. Okay. What is the advantage? It improves accuracy and reduces error, stabilizes the systems with negative feedback, and enhances dynamic response. That means when you need faster rise time, you need say reduced overshoot or something like this, then you can see that feedback control system is much more effective than open loop control, right. Okay. Now we will come for PID control. So we want to see, or we want to know what is PID control. The first term P stands for proportional control, second term stands for integral control, and third one is for derivative control, right. So it's a controller that automatically adjusts the control input. Yeah, that is the job of the controllers. What does it do? To reduce the error between the desired output and the actual input, actual output, sorry, what we want and what we are actually getting. We need to reduce the error between that, right. So the PID controller or the PID control law has these three components, where the first component stands for the proportional control, second one stands for the derivative control, sorry, integral control. So this is proportional, this is for integral, and this is for derivative. Okay. What is Kp? Kp is a proportional controller gain. Similarly, Ki and Kd are integral control gain and derivative control gain respectively. Okay. So how it is handling the error, right. We can see it here. Say there is a set point or reference input, which we say RT, output is YT, and it is coming through some feedback path. So here we get the error. What is the error? Error is ET, where ET is equal to RT minus YT. Fine. Now this is a proportional action. What it will do? It will take the error and then multiply with the proportional control gain. What will happen in integral control? It will multiply the integral control gain with the integral value of the error. And what happens in derivative control? Right. So that is what we were getting here. So error is getting multiplied by Kp, then integral of the error is getting multiplied by Ki, and the derivative of error is getting multiplied by Kd, right. This summation is happening here, right, and what it generates? It generates ut, right. It generates ut. What is that? It is the control input. Where does it go? It goes to the actuator of the drone, right. So this particular signal is ut, which is the sum of Kp into At plus this term plus this term. Okay. Fine. Okay. Now we will try to see all these components separately. The first one is proportional control, and how it contributes into the controller. It contributes by this term, right. So it reacts immediately to the present error. This is very important to note. Okay. More error, the proportional control will take more control action. If the Kp, the gain of the proportional control, is too high, then we get fast response, but overshoot may happen. Okay. If it is too low, then we will get a sluggish response. Okay. Fine. So when Kp is too high, then what is happening? A large Kp means small errors result in large control actions. Okay. So it can handle the small error and then it multiply with a large kp. So, finally, it becomes a large control action. This makes the system react faster, okay, because immediately it works on the present error. So, immediately there is some error, it will start working, and that is why it will reduce the rise time. Okay. I hope you remember what is rise time. If not, then please go back and study transient response from control system book, you will get to know. Fine. So, however, such aggressive control can cause the system to overshoot. So, that is a problem, you know, overshoot also as of now. So, if the system does not have enough damping, then the output can oscillate or even become unstable. So, these are the kind of consequences of having a high Kp. As an example, you see, if there is a drone altitude controller where a drone needs to maintain a certain altitude, if Kp is too high, then small drop in altitude, that means a very small error multiplied by a high Kp will give a strong upward thrust, and then what will happen? There will be one overshoot. That means where the drone is supposed to rise and maintain the altitude, it will go beyond that because of the strong upward thrust. So, this is what called overshoot. Okay. Now, if Kp is too low, then what is happening? Then the control action will become too weak to quickly correct the error. Okay. That means when there is a present error and Kp is very small, then immediately you can't handle that much error. So, the system becomes sluggish and there may still be a steady state error because low Kp does not provide enough force to reach the target. Okay. The system may be stable and overdamped, but not responsive. That means it can't respond immediately. As an example, if the drone is slightly below its set point, that means it should be here, the drone should rise and be here at this height, say height h. Only a small thrust increase due to low Kp. So, if it should be at height h, but it is not at that point of time, it is not at that height, but slightly below its set point, then only a small thrust can be increased due to low Kp. This takes longer time to climb from this height h hat to the final height h. Okay. So, we say that it is poor responsiveness. So, what we can conclude from here? High Kp reduces rise time, increases overshoot and possibly peak time, can reduce or have little effect on steady state error. So, adding Ki can be better in this respect, okay, that we will see later. Now, a low Kp increases rise time, that means the system will get sluggish and also may increase the steady state error. Okay. So, Kp determines the aggressiveness of the controller because it works on the present error, how much action it can take immediately, that is determined by Kp. Okay. And tuning of Kp is required for achieving a good balance of speed and stability. Okay. Now, we come to the next term, that is called integral control. What is integral control? We have seen that its contribution to the system is that it multiplies the integral control gain with the integral value of the error, right. Fine. So, it accumulates past errors, right. When we do this kind of error integration, then sometimes we do it from 0 to t. That means, when we are seeing the system at the time t, then it is accumulating all the past errors. It helps eliminating steady state error, a very important point for integral control. Acts slowly but persistently. Too high a value of Ki can lead into oscillations or instability. Okay. So, what happens when we have too high value of Ki? It aggressively accumulates error. So, even small errors also get added up or accumulated, which leads to a large control effort. Okay. So, it can increase the control effort. Okay. This can overcorrect the system after even minor deviations, which is very important, causes the system to overshoot. the set point often much severely, okay, and it can lead to oscillations or even instability, especially in the combination with a high Kp. So, we will see later that in this particular condition, when we introduce the derivative control, then the system or the situation becomes much better. Okay. There is also another phenomenon called integral wind up that might occur, which means that a large integral build up even after the system should stop correcting. Okay. So, because of its nature of accumulating past errors, this integral wind up occurs. So, in a drone altitude controller, if Ki is too high, a small persistent drop in altitude also will result into excessive and delayed build up of thrust. Fine. So, the drone surges upward past the set point. That means what? It will have some overshoot, as I have told that it causes the system to overshoot the set point, and there is a possibility that the response will be oscillatory in nature. Okay. That we will see in the results of one example in a later slide. Okay. So, when Ki becomes too low, then the controller is slow to correct the steady state error. Steady state error is very what should I say, it is not at all desired in the system, because when there is a steady state error, we can say that in steady state also the system is not behaving accordingly, right. It is not getting settled down properly, and we have some error. Now, small errors that persist over time are not correct effectively if we have low Ki. Okay. The system may settle below the desired output, that is also a very important point, especially in the presence of constant disturbance and model mismatch. Okay. The system response becomes too reliant on P, which may not drive the error to 0. So, when we do not have sufficient I, the system response can become more dependent on P, which may not drive the error to 0. Okay. Because proportional control is also to some extent responsible on getting overshoot, right. A drone that consistently hovers at 9.8 meter. So, this is 10 meter where it should be, but if it is at 9.8 meter, then may stay there indefinitely, then this drone may stay there indefinitely if Ki is too low. What does that mean? That means if Ki is too low, then the controller becomes slow to eliminate the error. Okay. To summarize, when we have high Ki, it reduces steady state error, very nice, but can increase overshoot and settling time, and sometimes it can destabilize a system which is lightly damped. Okay. I think as of now you know what is lightly damped system, and you can remember the symbol zeta, which denotes a damping ratio, right. Now, when it is a low Ki, it might be advantageous for stability, because the oscillation will come down, but it cannot eliminate the steady state error effectively. So, when the controller output is saturated, that means for a drone the motor thrust cannot be increased further, the integral term may keep on integrating the error, causing a much delayed and excessive correction in a later time, which is called integral wind up, and this is a very potential problem for integral controller. So, this shows that why just using integral control is not sufficient to control a system, and like Kp, tuning Ki properly is also crucial. Okay. Fine. Finally, we arrive to derivative control. This is the contribution of derivative controller into the system. It takes the error, derivative of the error, that means rate of change of error, and multiplies that term with the proportional controller gain Kd, right. It responds to the rate of change of error, fine, and anticipates future behavior, because it has the track of change of error, it can anticipate what will happen in future from the perspective of the error. Okay. It improves damping and reduces overshoot, okay, and it is sensitive to noise. Fine. When KD is too high, the controller becomes very sensitive to rapid changes in error. So, that is a problem sometimes. Okay. Even a small but very fast change in error also results in a large control action. Okay. Large control action means what? The energy consumption will go higher. Okay. It can cause high frequency oscillations, jitter, control noise. These are the problems. May counteract beneficial corrections by other terms of proportion and proportional and integral control due to overdamping. Okay. So, in a drone, slight sensor jitter in altitude, when we have altitude control, a very small or slight jitter can be mistaken for a rapid fall or rise, because there is a rate of change of error, and when there is sudden change, it can be mistaken as a rapid fall or rise in altitude. So, unnecessarily thrust change will happen, which is not good for from the perspective of energy consumption. Okay. But when KD is too low, the controller lacks predictive damping capability. So, the damping will not be sufficient. If we have low KD value, the system may overshoot and oscillate more in response to step changes. Heavily reliant on proportional and integral control at that point of time to stabilize the system, settling time may increase, okay, especially in underdamped systems. You know, when it's the system is underdamped, we have to tune we need to tune the damping ratio in a adequate way, so that we get a desired performance. So, when KD is too low, the settling time may increase, which indicates that the system is reaching steady state in higher time. Okay. That might not be desirable for many applications. So, without sufficient derivative action, a drone might overshoot altitude during ascent and then oscillate while trying to settle. So, that is the problem of low KD. To summarize, when we have high KD, it improves damping. When it improves damping, naturally it reduces the overshoot, but it is sensitive to noise. So, it can amplify noise and increase control effort if not filtered. Okay. However, when it is low KD, there will be less damping. Fine. Less damping means what? There will be more overshoot and longer settling time, possibly more oscillations. So, tuning KD is also important for stability and smoothness, especially in systems with fast dynamics. Okay. When the system is inherently fast, then the damping should be better. However, if we have a very high damping, then this kind of problems can occur. So, we have to find or tune the PID controller with proper values of Kp, Kd and Ki. Okay. Fine. Now, I would try to explain one analogy in terms of PID control for a drone example. So, just imagine a drone is hovering in a place at a certain height. Okay. Its task is to maintain altitude. Then it is a altitude control problem we were talking about in our previous examples as well. Okay. So, proportional control will do what? It will immediately correct the errors. That means, it works on present values of errors, right. It measures how far the drone is from 10 meter. If the drone drops to 9 meter, quickly the proportional controller will increase the thrust and will try to maintain the height. More error will provide more thrust, okay, but acts only on current error, may not reach exactly at 10 meter. There might be some problem of overshoot, that is why. So, there will be some problem of steady state error when it can't reach exactly at 10 meter. Fine. Integral control works on past errors. So, past accumulation of errors. watches how long the drone has been below 10 meter. Okay. If it's been hovering at 9.8 meter for a long time, I term builds up. It gradually adds thrust over time to eliminate the persistent offset. That means it will try to eliminate the steady state error, okay, or reduce it. But too much of I will give overshoot or oscillations. Okay. What does it mean? It needs to be stable at some particular height 10 meter, but with not properly tuned I, it might oscillate in this particular location. Okay. So, it will not reach the not be stable or maintain this altitude, but keep on oscillating like this. Okay. Now, what happens for derivative control? It's called predictive damping. Why predictive? Because it works on the future error by incorporating the rate of change of error. So, it reacts to how fast the drone is rising or falling. That is important, right? If rising too fast past 10 meter, it reduces the thrust, so that the drone comes down. Acts like a shock absorber, prevents overshooting and adds damping. You know that when the damping is added, then oscillatory nature of the system will come down. So, the drone oscillates less when we have properly tuned derivative controller. So, it improves stability and avoids oscillations. But the problem is that it is sensitive to noise, especially from sensors like barometer or IM. Okay. So, putting everything together, what we see is that P reacts quickly to current position, current error. I removes steady state errors that P can't fix, but D adds foresight, that means the predictive nature, and damping to prevent jerky motion, which leads into stability or decay in oscillations. Okay, fine. So, finally, if the PID controller is properly tuned, what we will get is a smooth stable hover exactly at 10 meters, even with wind or payload changes. So, it should be able to handle disturbance, it should not have overshoot, it should not have oscillatory nature in its response, and it should be very smooth and stable. Okay. Together what we are getting here is a fast, that means speed is improved, accurate, that means steady state error is reduced, and stable, that means oscillation is reduced. That is what we get with a properly tuned PID control in terms of drone altitude control. Okay. So, to conclude, we see that this controller output ut is the summation of kp et plus ki integral of et and kd derivative of et. Okay. These three terms get accumulated here and gives the controller output, which is the control input for the drone. So, the drone actuator will start working based on this control input. Okay. Now, we will see what happens if we do not have the derivative term, that means we have only PI control. Okay. We are not talking about PID now, rather we are focusing only on PI based control. So, of course, the derivative term which was there is now not there. So, what happens with Kp? It reacts immediately to the present error and provides fast response. What happens with Ki? It accumulates error over time and eliminates steady state error. No derivative term, that is why less noise sensitivity. However, if the system is very fast and oscillatory in nature, then not having derivative term will become a problem. Okay. So, why use PI instead of PID? When derivative action is too sensitive due to noisy measurements, then having a derivative control might be risky. When the system dynamics is naturally well damped, then we do not need the derivative component. In that way also we can rely on only PI controller and not on PID. Okay. Also, when the simplicity is preferred in implementation, then we can go for PI control. Applications: drones with filtered sensors. What happens here? Because of the steady state error for PI controller will be eliminated because of the influence of integral part. Response speed will be good from KP. Damping or overshoot control will be limited because we do not have the derivative term. So, we have to see that whether the system is naturally well damped or not, otherwise PI control might not be a good alternative of PID. Okay. Noise sensitivity will be low because we do not have D. Again, stability margin we have to check with proper tuning. When not to use PI alone? When the system has a fast dynamics, that means it is not well damped naturally, or it shows rapid transient response, then having derivative term is much beneficial to prevent overshoot and instability. Okay. Now we check PD control. So here we see we do not have the integral term, right? We have proportional and derivative. Okay. So it provides immediate response to the current error through proportional control. Large error means large control action or motor thrust that we have seen. And what happens in case of the derivative control? It predicts future error based on the rate of change, adds damping to reduce overshoot and to oscillation, right. So, what is missing here is the integral term. Because of the absence of integral action, it cannot eliminate steady state error. Okay. Fine, we will see all these cases in example. Why use PD instead of PID? When fast response with minimal overshoot is needed, then we should use PD because it is a fast response, but we do not want overshoot or higher overshoot. When steady state error is not critical, in those operations also we can rely on PD. If we have integral control, then steady state error will be ensured, but if we are not having, then we have to see that for which application we are using. If steady state error is not a problem for that particular application, then PD is fine. We do not have to go for PID. Okay. When noise levels are manageable or filtered, then also we can take chance of having PD control. Okay. And also with the systems for fast dynamics, we should use PD control. If steady state error is not a problem, then PD is sufficient. The application is an attitude control of drones, something like this. Okay. So, what we see here is that for using PD control, rise time is fast because of the proportional control, overshoot control is being done by KD, steady state error is not eliminated because we do not have integral control, noise sensitivity is moderate to high due to KD, the presence of derivative control, and stability margin improves. So, you can verify this part, that how stability margin improves for PD control. Okay. When not to use PD alone, when the system has a steady state error, we need PID or at least integral control. When we have persistent disturbances or sensor noise, then also we should not rely on PD itself, we might need one integral counterpart to handle the system. Okay. Now, we come to the example. Okay. We see that it is a drone system, we represent it like this. You have gone through the lectures and MATLAB implementation of transfer function. So, we know that when we have to specify one drone transfer function or plant transfer function, what is the plant here? In our case, the plant is the drone, right. So, we have the numerator and denominator, we put things accordingly, and if we write only this much in MATLAB, then what we get to see about the transfer function, it will be something like this. We consider mass is 1.5 kg, then damping coefficient or air drag is 0.8 and gravity is 9.81 meter per second square. Okay. So, you see the fast response, what is happening here? We have Kp equal to 10. So, we see that system is responding very well, very fast, but there is a steady state error even after 9 seconds or so, and since there is no KD, then what is happening? We see one oscillation in the response, right. So, what do we need to do for this? When there is oscillation, we have to increase the value of KD for having a better damping facility, right. And when there is a steady state error, what needs to be done? We have to improve Ki as well. Now, this is very much application specific. We do not know how much oscillation is tolerable, how much steady state error is tolerable. So, we have to check the system requirements or desirable performance properly, and on the basis of that we have to fix or tune the PID controller with proper Kp, Ki and Kd values. This is something which we are doing blindly as of now. I would not say blindly, I am just showing you things that what is happening when we have this particular set of values or parameters. But for a proper practical system, depending on its other specifications, we have to tune the PID controller properly. Okay, fine. Now, what we do here is that in the second example, we increase the Kp, Kd from 0 to 2. Kp remains unchanged, Kd is increased here from 0 to 2. By doing that, we see that the derivative counterpart actually imposes a damping into the system. That is why now the oscillation is reduced. What it was before, compared to that, having a derivative term has reduced the oscillation. So, we can conclude that it is going towards stability. But the problem is that we have a Ki of value 0.5. So, for that there is a steady state error. What is the steady state value with a step response? We are seeing step response of the system, right. Now, what is the steady state value? The steady state value is 1. Okay. So, ideally the response should somehow get settled to the value 1, right. But what we are seeing here is that it is not happening, right, and there is some steady state error. Right, this much error is the steady state error which is coming because we have low Ki. Fine. So, we go to the next example. We keep Kp unchanged, we keep Kd unchanged, and we increase the value of Ki from earlier it was 0.5, now you make it 5. You see now there is no steady state error, it has come to exactly 1, right. So, we can say that the steady state error is 0, right. So, this is how we can check different performances of the drone altitude controller using PID. We change the value of Kp or we change the value of Ki or Kd, the system performance will change. Now, what we actually desire for the system or for the particular application, we have to fix Kp, Ki and Kd value accordingly. Okay. So, what is the limitation of PID control? It is purely reactive, does not use a model of the system, cannot predict future behavior beyond what the derivative term infers, struggles with nonlinear systems, handles linear systems better, but in real life we get more nonlinear systems than real systems, poor adaptability as gains are fixed. This is something very important because when we use the controller for some application, we fix the gain Kp, Ki and Kd. Since it is fixed, the adaptability to the environment of the controller becomes restricted. Okay. Needs careful tuning. I have already told that we have to tune Kp, Ki and Kd properly. From the example, we have seen that how changing the values of Ki and Kd fixes the system, right. But what we have not shown is that how to get a proper Ki and Kd value, right. So, it needs careful tuning. PID cannot enforce actuator limits, that means if there is a limit by motor thrust, then PID cannot overcome that and it needs to like be obeying that, and it cannot enforce actuator limits separately. It cannot impose safety constraints. We will see the concept of safety later in terms of obstacle avoidance when we talk about the path planning of drones. That time safety constraint will become clear. Also energy or fuel minimization directly PID cannot handle. So, these are some kind of constraints which we have to do in terms of optimization. Okay. And what we are doing in PID is not the same thing. So, PID faces certain problems in enforcing these terms or this criteria. Okay. Now, there are tuning methods like manual trial and error. What we were doing, right? What we were doing is actually manual trial and error. First, we see that it is an oscillatory response. We increase KD. We see that the oscillation is coming down, but there is a steady state error. Then we increase Ki, but we are not properly tuning the controller, because see, when we make KD from 0 to 2, we do not know whether 2 is sufficient or not. When we make Ki increase it from 0.5 to 5, we do not know whether 5 is enough or little lower value is also fine. So, tuning is required. Okay. So, manual trial and error is one process which can fix the problem, but it might not be always very intuitive and can be tedious. Okay. There is one very popular method called Ziegler-Nichols method, which is a heuristic approach to tune PID controllers based on the system response and oscillation, critical oscillation. Okay. So, that is something is out of the scope of this particular lecture, but in the reading materials which I will be telling later, you can go through and talk about. Okay. The third point of tuning method is auto tuning tools, which is available in MATLAB website, and you can go through, then you will understand that how PID tuning works and how PID auto tuning for a plant can be modeled. Okay. Fine. So, I would summarize the lecture here at this point. What we are seeing here is a feedback controller, which is popularly known as PID controller, and it has three components: proportional, integral and derivative. Proportional control works on immediate correction based on the current error. Integral control accumulates past error to eliminate steady state offset, and derivative control predicts future error by incorporating the rate of change of error and thereby improves damping. Okay. So, when we improve damping, then the system goes towards stability or decay in oscillation. Okay. So, we understood the role of each terms. We have seen that the PID variants like PI and PD, in which conditions they are sufficient and how they work. Then we have gone through examples of drone altitude controller, and what we can conclude is that PID is simple, versatile and effective, but the only thing is that we have to take care of the tuning part. Okay. For a practical application, without tuning, using PID might not be very much helpful. Okay. These are the reading materials you can go through. These are very like classic textbooks of control systems, which will make you understand what PID control is and how it works. So, with that I would conclude this lecture. Thank you. See you in the next lecture.